Yeah, so my title is Taking a Spacewalk, which I think is the best pun I've ever made. So it's a hashtag I use mostly on Twitter to describe women of color in planetary science. There are women of color in planetary science. You might not see us. But I think especially with my generation and also the next sort of group of people coming through undergraduate degrees, we're growing in number, and I think we're growing in voice, and that's something I always like to center. So I also wanted to point out this background. So this is a giant, this is a giant river channel on Mars. So this is maybe a kilometer or two away from Curiosity rover. And right now we're looking on a perspective view. So this is the bottom of the channel, and this is north, and this is a little island that may have been formed by this river changing direction at some point. And there are all these really amazing exposed layers. And so this information is actually 25 centimeters per pixel. And the reason why I want to open with this is that there's no moment in planetary science, I don't think, at least personally, where you don't have to sort of grapple with what you're doing. It's very easy to feel very small and also very big, because you get to play with planets in a way that is a bit unnatural. So as a geologist, when I see this, I kind of think, one, there's a lot of amazing detail here. We don't get these kind of images of Earth. We actually have more satellites around Mars studying at a higher resolution than we do for our own planet. The second thing I feel is I'm never going to be able to see this in person, and I think that's extremely humbling. So that's just something to think about to open. So this is where I started. I think I'm 6 or 7 years old in this photo. So there are two things that fuel me today. It is this person right here. So I was always interested in physics. My dad was an engineer. So he did his degree in the UK. He moved to the US. The US said, your degree doesn't make, isn't a qualification here. So he had to start from scratch, and he built computers in our basement. And I used to watch him work, and he would help me out with science fairs. The other side of that was, I told my mom when I was 4 years old that I wanted to collect rocks for a career. I said, how do I collect rocks for the rest of my life? She said, be a geologist. And so I just borrowed every single book I could from the library about geology. Didn't know what it was. I thought, I just want to collect rocks. And I thought it wouldn't be a career. I just thought that doesn't really make any sense. I also wanted to be a writer and an artist. And so my idea was I would write children's books, and that would somehow fund my research, which is very funny. It's quite the opposite now. The second thing that drives me is this image, more so on the right. So I think I was 10 years old when I saw this image. I saw it on TV. It was a documentary about planetary geology. So these images were taken by the Huygens lander in 2005 of the surface of Titan. So this probe detached from the Cassini spacecraft landed on this planet, and it's the farthest out we've landed on a planet, or a planetary body rather. And the amazing thing about this image that resonated with so many people is that this just looks like home. These rocks are nice and rounded. They could have been formed in rivers, and they probably did. Here are views from the descent. There's a river delta. It's a little difficult to see with the perspective. So we found out that Titan is sort of exactly like Earth in having a hydrological cycle, except it's driven by methane. And so when people saw these images, they thought, okay, here's a world that we can relate to. And I was really angry when I saw this. As you can see, I was very angry because I thought, 2005, I'm 10 years old. I was a precocious 10-year-old. I'm 10 years old, and I didn't hear about this mission. We didn't learn about it in school. There was no big day of, we just landed on a moon of Saturn. And I thought, that's the worst thing in the world. I need to change that. And so that's what stuck with me. I think I'm still angry about that. I'm really, really angry about that. Like, any kid should be able to look at this image and think, that's a moon of Saturn, and it looks like my backyard. Yeah, my eyes were on the prize. I sent NASA to my homepage. I told my parents, I want to study rocks on other planets, and they had no idea what to do with that, because did not have any education in the US. They had no idea like how to guide me. They just said, just do it. Just figure out how to do it, and we'll support you, which was amazing. But the takeaway message from that for me has been that space is for everyone. Space currently is not for everyone. It's very guarded in institutions. It's very inaccessible, I think, to people, where Mars rovers, I think, sort of changed the game, where NASA specifically and also ESA have really pushed to make Mars relatable to people. But in the end, most of what we do as planetary scientists doesn't reach people. But this is our neighborhood, you know? Every child should be able to look at this and think, that's my neighborhood. We belong to space. We belong to the solar system. So that's what sort of drove me from a young age. I didn't really have those types of words. I was just really angry. So being very angry, I don't know how I did it. I found this online learning community that has now been defunded because the government keeps taking money away from education in space science. But I landed somehow at this internship in high school at NASA Goddard Space Flight Center. So this was working on using laser altimetry. So here in the background, this is a laser altimetry map of the moon. So essentially, lasers fired to the surface of the moon, Mars, or Mercury. And the return of the signal is timed, so you can map out the topography of these bodies at high resolution. So I was using that instrument to actually look at reflectivity. So this was a crash course in space research and missions. I was 16. I had no idea what I was doing. It was the time of my life. As you can see, I'm really, really happy. Also still really angry. And here are some of my results. I found my very first presentation a couple days ago. It was the cutest thing. So the idea is that there's this instrument. It receives light at a specific wavelength, but it's constantly receiving light from the sun as well. And so the idea is that all that sort of noise is actually sunlight bouncing off the surface of a planet at that wavelength. So I applied that to Mercury and tried to map reflectance at that specific wavelength, 1064 nanometers, which can be compared with actual spectroscopy instruments on board this mission. So this is MESSENGER. So I didn't really want to dwell on that. One thing I wanted to say actually earlier. So I think especially for women in science, we get so used to sort of talking about our accomplishments in a sort of CV manner. And I was writing this talk and I thought, I don't really know like what the narrative is of my career. And I thought so much of what happens, I think, especially with women in science, is that the details are all in between the lines, right? So that's kind of something I want to emphasize. So this project was great, you know, it was a research experience. It was also really, really terrifying. I was a 16-year-old surrounded by adults at NASA, and I learned a lot about space science, and I realized I wanted to pursue it. It was also really scary because I was still one of the only women at NASA, and I was a child. And I think that stuck with me. I mean, most of the interns were girls, and I think that's also a huge takeaway. So there are a series of internships that I did, and every time there were a lot of girls, but every year there were fewer. So towards undergraduate degrees, there were fewer. Once I got to graduate school, there were fewer. So the second thing I did was that horrible resolution image, was a National Science Foundation project at my university, University of Rochester in New York. So I was looking at these things, which are very small. They're called impact glasses. So they form when really high-velocity asteroids impacted Earth, essentially vaporized material, and the rock reformed as glass. And the idea is that during that vaporization, you're getting separation of charge. There's plasma. So there should also be a magnetic field produced by that. And that's really important when we have spacecraft that are impacted by micrometeorites, because those magnetic fields can disrupt electronics. But experimentally, we don't really have that kind of evidence. But increasingly, we're using methods to study rock magnetism to be able to figure out whether impacts generate magnetic fields. And that was something I was able to do. So that was at University of Rochester. So after this, again, to be in between the lines, and I wasn't sure how to make it into a slide, I got really, really sick. So everyone who I talked to today about like why I couldn't eat the food at lunch, again, like please don't worry about it. I got really, really ill in at university. It was an autoimmune condition. So again, I was fueled by all this anger as a little kid. I wanted to study space. I wanted to study our environment. I wanted to make it accessible to people. And all of a sudden, my body just said, no, you have to stop. So I had to leave university twice. I think I almost died the end of my degree because of my condition. And the one thing I think that helped me get through it was actually thinking, I still need to do this. Like, there's no one else who's going to do it, which is not true, but and that's something that has continued to drive me. So the next thing I did was the NASA Academy, which was a 10-week research intensive. So it was a research project, and it was also a mission proposal simulation. So we had to design an entire mission, propose it to NASA administration. Very frightening. So our idea was to look for lava tubes on Mars. The idea being that lava tubes are giant cave systems on the Moon and Earth, and potentially on Mars. And they're at a sufficient depth to protect people from radiation, cosmic radiation, solar radiation, and temperature flux on Mars. And they also may have stores of water ice. So really useful when we're thinking about human exploration of Mars. So yeah, we took a very cool photo. Still the best photo I think I've ever taken. The concept was about 5 or 6 satellites, so using ground-penetrating radar. And they essentially cycle through between transmitting and receiving while firing at the surface, and then they combine those measurements, so that either using interferometry or synthetic aperture to achieve a higher resolution by having multiple signals. So we're looking at a 50-meter depth, so we're thinking what is feasible for human exploration. And so my job as sort of geology lead was to find a region of interest, which was Elysium Planitia, which is shown here. So this is a huge volcano, and this area possibly was an ocean at some point. So there's really interesting potential geology of interaction between volcanic materials and water, which can produce organic molecules. So focusing on these lower slopes up this volcano, which actually extends quite far, thinking about where lava tubes shallow enough and also at less of an extreme angle could be for human exploration. So that was just the concept that we did. The NASA Academy was a big learning experience. Again, I said every year there were fewer and fewer women in the programs that I did. So we had 4 women in this group and 2 women of color. And I think that was one of the most recent diverse groups of people I've worked with in planetary science, which is very sad. I think something else that the Academy taught me was not everyone is open to the message of making space open to everyone, which I won't get into detail here because I can't, but something to think about. So thinking about work I'm still doing, so I started this at the SETI Institute, which is the institute that was looking for aliens, but it was not looking for aliens. NASA Jet Propulsion Laboratory, and also remote work presently. Looking at icy moons of Saturn using 3D images. So this is ongoing work, again, towards 2 papers. So here's just a really quick crash course into icy bodies. So we have 4 moons here, these 2 of Jupiter, these 2 of Saturn. These are really diverse moons. They undergo really extreme geology because of the gravity, magnetic fields of Jupiter and Saturn. So essentially these bodies, if they have an eccentric orbit, that means that at some point they receive more gravity on one side than the other. And then as they move away, further away from the planet, they compress again. So that's a lot of shear heating happening in the subsurface, which means we can have the potential for subsurface oceans. So Enceladus is confirmed to have a global subsurface ocean. We've sampled plumes coming out of this ocean that suggest that there are hydrothermal vents on their floors, that they're potentially salty, that they contain organics. So this is really an amazing place to think about. I actually have not studied Enceladus, but I love it, so I'm talking about it. Europa is very similar, much bigger than Enceladus, and potentially more water than Earth, 2 times as much water as Earth. And Titan, as I've mentioned, entire hydrological system, but methane-based, but with really complex hydrocarbon chemistry. So this is sort of pushing the boundaries of what we think life might look like and where it might survive. Io is very cool. Probably life doesn't exist, but it is the most volcanically active place in the solar system, to our knowledge. So here's Mimas. Here's Mimas around Saturn. Here is the Death Star. We call it the Death Star moon. So because of the gravity and flow of material, which we call rheology, features like craters, so like this big crater right here, which is called Herschel crater, relax or flatten over time. So this is a function of geophysics, chemistry, and so heat and composition control the rate of relaxation. And this can actually tell us about oceans. So say we have a very hot ocean close to the surface. We have lots of craters on the surface. The convection that's happening here is going to cause a very high geothermal gradient in this ice shell. And that ice is actually going to flow out to achieve equilibrium more quickly and thus flatten craters out. So that's the general idea. So if we can model that and compare to current crater size, we can actually figure out whether a moon had an ocean, potentially still has an ocean, and how long that ocean has endured. And one way we can do that is actually just looking at craters using 3D images. And I'll talk about 3D images a little more in a bit. So this is the work that I've done. It doesn't really look like anything, but this giant basin is one of the biggest basins in the solar system. It's 400 kilometers across, which is about the distance between London and Dublin, I think, 460. So this is a digital terrain model. So stereo images, we can process them into these 3D models by taking overlapping images taken from slightly different angles. So it's similar to how human eyes figure out depth. Our eyes are separate by a slight angle, so we're getting slightly different angular information, and we can resolve the 3 dimensions. So 3D processing can help us achieve that. We can actually make a 3D image, which is what this looks like, which is quite ugly, but I'll show you a really pretty one in a minute. And one thing we can do, so if you're a geologist, you know what these are. If you just draw a line across it, you get a topographic profile. And that way, you can measure craters. So I've actually measured over 100 craters on 4 different moons using these 3D images to figure out their current sizes and also look into how we can statistically determine what they used to be shaped like. And that way, we can calculate relaxation if we think about initial depth minus, or the change between the initial depth and the final depth as relaxation. So that's the paper that I'm currently working on. But for now, I'm a full-time PhD student at UCL's Mullard Space Science Laboratory. So we're out in Surrey. We're actually not in London. We're in the middle of nowhere, probably a 30-minute drive from any local town. Beautiful, really, really quiet. And I'm working on 3D imagery of Mars. So finally, through all of this, I've ended up at Mars somehow. So I wanted to continue thinking about planets in 3D, especially for geology, because of this thing, the sort of anger I have about access to planetary information, where I think 3D offers something more intuitive to people than just 2D images and 2D mapping. So making geology actually relatable to human beings, which is actually very difficult. So as geologists, we think in 3 dimensions. As people, we think in 3 dimensions, especially when we're out in the field, when we're measuring rocks, when we're measuring layers, when we're even just understanding the environment around us. And remote sensing data is 2D map view information, which, again, is not intuitive. It's just not how we work as human beings, especially as geologists who've trained out in the field. So my goal is to figure out how to best develop, but also view and manipulate 3D imagery as scientists and for the public. So this is that channel again, and I'll talk about how we got here. So first, essentially the first 2 years of my PhD, I've been processing new 3D images of Mars from 3 different orbital cameras. So I've been focusing on this crater, which is called Gale Crater. It's about 200 kilometers across. And it's the site of Curiosity rover. Curiosity is just around here. We don't actually know because I'm not privy to that information, but it's somewhere around here. And I'm really interested in how these different data sets can be combined. So we have global coverage of Mars at pretty high resolution. Again, we study it more than we study Earth. We don't have enough people to do that, by the way, so if you're interested in studying Mars, like, great time to do it. But it's not actually that high resolution if we want to really study fine features, especially towards the scale of a rover. So we really need to combine high resolution, very limited coverage with lower resolution to contextualize local geology and also look at these fine features in a greater context. So here's a zoom in. So this is 25 centimeter per pixel data that I've fused with 6 meter per pixel data, which is quite a big shift. And Curiosity, again, is somewhere here. I'm not allowed to know where it is. But and so if I process this in 3D and then combine these, we can actually put it in a 3D environment. And this is just a little clip of what the environment looks like. So this is a great tool used by NASA. It's totally open source. You can download it. And if you want to download it, let me know. So right now we're looking, Curiosity is over here. And it's currently trying to drive up all the way up here. So we only have this limited high resolution data over this area, but it lets us sort of see the broader terrain of where the rover is going. But it's also really great for just understanding where the rover is. Because we hear about, okay, the rover is exploring this outcrop. What does that mean? But when we look at this, and it's black and white, which is limiting, but you can kind of see, okay, water flow down here, right? That's pretty intuitive. These look like hills. This is a little ridge. If you put a scale bar in, or even a person, which is what I'm trying to push for, you can figure out actually how big things are and imagine yourself there, which I think is important. So here is one thing that I did in the software. So I dropped a camera. So this tool is actually used to plan rover operations. You can drop a camera and plan an image you want to take. Of course, we're not the rover team, so we can't do that. But I dropped the camera and I looked around and I matched it with an actual rover image that was taken. You can see it sort of, it's easier for humans to sort of correlate these two images and figure out where the rover was when it took it than just looking at a 2D map. So this is very important. This is how some of localization of rovers work, but it's also really great for kids. So one of the things I've been doing with this tool is actually I've designed a number of games for children from age about 7 through 18 to figure out where the rover took images. So I don't use Curiosity, but I use a different rover, where I give them the 3D data set, and I give them the rover images, and I teach them how to use the camera, and I say, find where the rover took the images. And every single time, whether they're 8 years old or 18, they do it way faster than I do. And I think that's pretty incredible. They pick up what this means because they know how a camera works, but also because it's in 3 dimensions, and because they can understand the sort of world around themselves and put themselves in it, which I think is really powerful. And I think the most powerful thing to come out of my PhD, because I don't really care about the data sets in the end. I care about whether someone understands this is Mars and you're allowed to look at it. So another area that I've looked at, so I've shown you a preview of the channel. So I'm really interested in these layers that are exposed because they can tell us about the history of this feature right here. Total mystery about what it is, whether it formed volcanically or through water action or glaciers. And so here it is in 3D. And I've shown, so I'm involved with the ExoMars team, and I've shown them a lot of 3D visualizations before, or my group has. I think this one had the biggest impact because it was just a team of geologists standing around saying, wait a minute, this looks like that. This looks so familiar. This looks like that place I went to in the field. What is this feature? It looks like a meander that, or a secondary flow feature or something. And I think that was also powerful. So let's actually look here. So this is a tool being developed for ExoMars, where we can actually put rover imagery in here and do measurements. But I decided I wanted to look at this channel in the software. So I've been measuring these layers. So these are dips and strikes, which are just a representation of the orientations of these beds. And this can tell us about the relationships of the beds to each other, which can tell us how they formed, how they were deposited, whether it was water, wind, glaciers, volcanism, that sort of thing. But I wanted to end, I think, the ultimate lesson, and I think I've sort of spoiled it. Space is for everyone, but is it right now? Images, like space, are not free of systems of power. So I get to show this to people, but they can't find it themselves. And that's a system of power. I get to show this and explain it to even other scientists, and they don't have access to it, and that's a system of power. Why is this incredible place, this huge channel, which is 2 kilometers across if you want scale, that is so familiar to us? It's a way for us to connect instantly to Mars, but it's hidden away in the academy. So that's something that I'm currently thinking about. It's something that I've spoken about elsewhere, about how we can think about images as a way to democratize planetary science, especially when we're thinking about it in 3D, which is accessible to people. And that's sort of totally irrelevant to my PhD, but I'm trying to work it in as a chapter, so we'll see. And that's really all I have to say. So thank you, and I'll end you with this very angry child.